Hello everyone and welcome back to your YouTube channel and welcome to this fantastic video of today. As you must be aware, we are working with this module that is called electromechanical conversion systems. And one very important aspect of those electromechanical conversion devices is the magnetic material properties and how those magnetic properties provide insight about the performance of the whole conversion system. So today I have a very practical and very simple, a very interesting numerical example related to the magnetic material fundamentals. And in this case today, we are analyzing a ferromagnetic material, an excellent ferromagnetic material that is used in a magnetic circuit. And the plan today is that you will learn about the very important properties like the reluctance, the Hawkins' law, the MMF, and so on. So without further delay, let's start this video today with reading this very important statement over here. So, as you can see, there is a magnetic circuit that is represented here in figure Q1. And basically there is a winding with 500 turns and there is a current I that is establishing this magnetic flux that is moving between two different materials. I believe all my students, they can see that there is a very good ferromagnetic material here where the flux lines are moving, but also there is a small empty space over here that we call the air gap. So we are assuming that here the majority of the magnetic core is excellent ferromagnetic material. You can see that the relative permeability is numerically equal to 70,000. That is a lot, is an excellent, a magnificent ferromagnetic material. And now we have this small area over here that we have the air gap, and we will neglect the fringing effect at the air gap. In other words, when the flux is moving from the ferromagnetic material and moving through the air and going back to the magnetic material, we will assume that all the lines go straight. There is no losses or fringing effect in that process. Also, we know that the magnetic material has a square cross-section and the area is 9 square centimeters. And also the air gap has, of course, the same cross-section, 9 square centimeter. And the total length in this magnetic core is 30 centimeter. That is very, very large compared with the small air gap that we are having over here. The air gap length is extremely small over there. You can see 0.05 centimeter. So we have here three questions, three very valid and important questions. The first one is to calculate the reluctance in both materials. In this case, we are calculating the reluctance in the core and the air gap. And if you want to attempt this problem, you can see over here the numerical solution, the numerical answer. And then we have a condition that say, considering the magnetic circuit is working with a magnetic flux density of 1.0 Tesla. Question B, determine the flux in the magnetic core. Remember that we use this Greek letter over here for the magnetic flux and the unit is Weber. And you can see the numerical answer there. And final question is C, determine the electric current I that is applied in the winding. And in this case, we want that current in amps, okay? Just a quick remark over here for everyone. 1 square centimeter is equal to 0.0001 square meter, okay? So let's start the solution of this very basic but very nice problem, okay? So let's go here. The first element that you need to remember from your classes, from the theory, is that we have a very interesting magnetic property that is called the reluctance. The reluctance is similar to the resistance. Resistance is a property for a macroscopic property for the bodies and is used for electricity and is telling you how easy the current can move through a device. So similar condition can be applied for the physics related to the magnetic field. The property received the name reluctance. The reluctance, you can imagine that is similar to the resistance, but in this case is allowing the flow, the flow or the flux moving in the material. If you look this equation over here, this is the equation for the reluctance. You can go and watch the videos related to the theory, but the reluctance can be defined in terms of the geometry. For instance, in the numerator, you can see over there the letter L that is representing the length of the magnetic circuit, and the letter A for alpha represent the cross-section area where the flux is moving. And finally, the Greek letter mu is used to define the absolute permeability. The absolute permeability is quite interesting because it's the product between two very important elements. One of them is mu sub r, that is representing the relative permeability, and also mu sub 0, that is representing the permeability of the vacuum. And all my students must remember that the permeability of the vacuum is a constant, and that constant is numerically equal to 4 pi 10 exponent minus 7, and the unit is Henry over meter, okay? So now the plan is to use this equation over here in order to calculate the reluctance of the magnetic core and also the reluctance of the air gap. In other words, we will represent the magnetic interactions of this material by the reluctance of the core and the properties over here by the reluctance at the air gap. Now it's question to define the proper geometry and also using this equation. You can see over here the equation is the reluctance of the core. We need the length of the core that in this case was already defined, and also we need the cross section of the magnetic core, and in this case, remember, we convert from a square centimeter to a square meter because we need to use this equation in the MKS system. So finally, and what is extremely important for you is that this is mu sub r, that is very high, in this case is 70,000, and is coming from a very good ferromagnetic material. And here we have mu sub 0, that is basically the permeability of the vacuum. When we put the number together, you can see over here we have the first answer. The first answer for the question A, and is a total of a reluctance that is slightly over 3,700 amps terms divided by Weber. So next step is to do something similar for the air gap, but the main difference is that the length of the air gap is extremely small. You must remember that is so small, that is 5 exponent minus 4 meters. We have the same cross-section area for the air gap and also for the magnetic material. And the very important relationship over here is that we will use the permeability of the vacuum because the air gap is an empty space and we are assuming that that is a free space. So the relative permeability of the free space is 1. So finally, the absolute permeability is 4 pi exponent minus 7. Now it's time to put the number inside the equation. This small length over here, this small cross-section and the permeability of the vacuum. And finally, we get over here the results of the reluctance coming from the air gap. Something that is extremely important that you need to understand is, you can see over here how the reluctance of the air gap is extremely high compared with the reluctance of the magnetic core. And that is because the magnetic core has a high relative permeability, and that means it's allowing easily the magnetic flux to move through. That is not the case for the air gap. The air gap is the vacuum or free space, so in that sense the magnetic properties are really poor. So as a consequence you will have a permeability that is extremely high. For the next question, well, what we need to do is basically calculate the magnetic flux. Remember that we are using this Greek letter over here, and the magnetic flux is related to the magnetic flux density, letter B, and the cross-section area AC. So to calculate here the magnetic flux, basically we use this relationship. The flux is equal to the magnitude of the magnetic flux density multiplied by the area, cross-section area. And when we put the number together, well, we have here the amazing numerical result. You can see over there, 9 exponent minus 4, and that is the Webers that is inside this magnetic circuit, okay? So now we have the flux, now we have the reluctance. So the final question is, how much is this current? And to obtain this current, what we need to do is think about this geometrical property over here, this geometrical configuration as similar, something similar to a circuit, okay? So what I would like to show you now is the equivalent magnetic circuit. If you look here in this figure 1 over here, you can see that we have in this figure a magnetic flux, and this magnetic flux is similar to this one. In fact, it's the same, that is moving inside a closed loop. And inside this closed loop, there are two different materials. There is one material that is coming from a very good ferromagnetic material, that is the magnetic core, but then we have this small empty space over there. So what I am telling you is that this reluctance over here is representing this section, and this reluctance over here is representing the air gap. And finally, something that you must understand is that you need something creating or establishing this flux, and that is coming from this winding. So in any magnetic circuit, when you have several windings, you will have the same number of sources inside the circuit. In this case, we have a single source because we have a single winding. So now we have something similar to a circuit, to an electrical circuit. And now what we need to do is apply properties that allow me to calculate or to obtain the flux in this magnetic circuit. So what you need to remember is the relationship between the MMF and the flux is defined by the Hawkinson's law. Hawkinson's law says that the MMF, or magnetomotive force, is equal to the flux multiplied by the reluctance. And in this circuit, the flux is moving by two reluctance over here. So we use the name series magnetic circuit, and the total reluctance is identical to an electric circuit, is the sum of the core plus the air gap. So if we put this inside this equation, we obtain here the equation number 1. The MMF will be equal to the flux multiplied by the total equivalent reluctance, in this case the sum of the two materials. On the other hand, we know that the MMF The MMF is the product between the number of turns and the currents producing this or establishing this magnetic flux over here. So from this equation, we can extract the current, and now we have a second equation that we can combine together. So over here, we have this beautiful equation, and this beautiful equation allows me to calculate the current. The current in this winding will be the division between the MMF by the total number of turns. But remember, the MMF is the product between flux and reluctance. So the numerical substitution is done in this equation, and finally we are able to obtain the current in this winding. And as you can see here, we have a numerical solution. The total current in this winding is 0.8026 amp. So now we have calculated the current, the answer for question C, and that is the ending of this problem. However, before we finish this exercise, this video, I would like to remind you that in this video we learned about magnetic properties, and these magnetic properties can be represented by reluctance. Reluctance is basically a property, macroscopic property that depends on the geometry of the body, but at the same time of the permeability of the material. And at the same time, we learned in this video that any physical configuration establishing magnetic properties can be represented by something that we call magnetic circuits. And from magnetic circuit, well, all my students, they are extremely clever, they are genius, they understand circuit analysis for electrical circuits, so they can do something similar for magnetic circuits. Instead of using Ohm's law, we will use the Hopkinson's law, but the problem is solved in that sense. So this is the end of this video. I hope you enjoyed the explanation. I hope that you understand these very important concepts and you are able to apply them in your real life. Thank you very much for watching, and I will see you at the next video. Bye now.